Good afternoon. Welcome to Citrus and the Banatow Institute. We're really delighted to have you here this afternoon. My name is Camille Crittenden. I'm Deputy Director, and pleased to welcome you to the Citrus Research Exchange talks. These happen most Wednesdays at noon, and we're happy to provide lunch if you sign up in advance, as we were just discussing. But wanted to also remind you that everything everything is compostable. So you can throw everything in the green bins in the back when you're done. A couple of quick announcements before I introduce our keynote speaker. We're really pleased to also webcast these events, and so I want to welcome our web viewers, whether you're watching at one of the other Citrus campuses at Davis, Merced, or Santa Cruz, or at home or in your office, or later. These will also be archived on the Citrus YouTube channel, so you can refer to them later. One other announcement about the Big Ideas competition. This is sponsored through the Blum Center, but Citrus is also a sponsor of the category of IT for Society. If you take a look at the Big Ideas website, there's a lot of information about that opportunity, and there will be a Google Hangout about it later this afternoon at 3 p.m., an info session. So I encourage you to take a look at that. So we're really delighted to have Professor Kenichi Soga here to speak to us this afternoon. Kenichi is new as a professor to the Berkeley campus, but is returning since he did his graduate work here some years ago. He's the Chancellor's professor in civil and environmental engineering here, and was professor of civil engineering at the University of Cambridge before coming here just this year. He works on geomechanical processes, innovative monitoring, and environmental geotechnics. And so I look forward to hearing his remarks. Welcome.
Yeah. Thank you very much. Well, first of all, thank you very much for coming to this particular talk. I'm very delighted that you're all here because it's very important for me as a new professor really to introduce what I've been doing the past 20 years at Cambridge. And of course, before that, I was at Berkeley doing my PhD, so I'm very happy to be back over here. What I'm going to do today is really to give you what I call smart infrastructure and construction, really about how to make our infrastructure in civil engineering more attractive to other peoples in the world. And actually, about 5 years ago, I set up with my colleagues Cambridge Center for Smart Infrastructure and Construction. And that's the work I'm going to show you is very UK-centric, unfortunately, because I just moved here. But I'm hoping that things will happen over here in California, in the US, in a similar way. Before I do that, many of the things I talk is really outcome of the paper I recently wrote my colleague, Infrastructure Sensing, from the Royal Society called Interface Focus. So if you're interested in that, I can upload, and then if you can email me, I can give you the paper on this particular about this particular paper. I thought it'd be good to give you lots of examples about infrastructure, so at least as you will understand what the issues in civil engineering. This is City of London. For those who may be to London, you see a River Thames. And then this is a famous building called Shard. And then here is called London Bridge Station. And they're doing a 5 years renovation. It started in 2013 and going for a 5 years renovation. The London Bridge Station is one of the oldest stations in London. And you can see that there are a lot of passengers per day, and a lot of people use this particular station. The challenge is that this renovation is done as the construction or renovation is done in 5 years' time. So trains are working as well as construction is happening. So it's a very busy station. As I said, London Bridge Station is one of the oldest stations in London. Of course, in San Francisco, we have older things, but also in London, there are even older things. And you can see that 1836 it started as a sort of a purple part and keeps on expanding. And you can see how it started in 1836 and then how it looks like right now. And then in 1970s, the one that when they said, okay, let's try to change the station dramatically. So London Bridge Station was last redeveloped in 1970s. And in 1972, they had a vision of this particular, trying to change the station. 2 old rail stations will be merged into one with a higher capacity, giving easy interchange between buses, tubes, and trains. So mixing with bus and tubes and trains. And as you know, tube is subway. And direct access to all service from spacious concourse with new bars, buffets, and shops. So bringing all things together. 2012 is right now, there's a new renovation happening over at London Bridge Station. And the vision over that says the number of platforms will increase and track layout will accommodate higher capacity trains. At the same time, existing bus, train, underground service, like Tube, will link to larger concourse in the UK, which will offer variety of retail service like bars, buffets, and shops. So again, after 40 years, they're saying the same thing. But we tend to be in civil engineering, we tend to design our infrastructure 100 years, 120 years design life. So there's a mismatch between how we use our infrastructure and how we design our infrastructure. Think about this as a population of London. I stopped here until 1970s when they were doing this first big renovation. So London population was going up, and after the World War II, it started to decline. You're over here, how do you want to predict? So then you start to say, okay, what's going to happen to the next 100 years? But what really happened to London is that it went like this. And these are the predictions. So you can see that how we predict over here, and then the usage of the station changes as the economy changes. But then we tend to design 120 years. So there's a mismatch over there. Again, this is a prediction after, as you know, Brexit. We don't know what's going to happen. So again, that's the difficulty we have. So our 100-plus design era concept may be compatible with the actual demand in the future. Is it? And then making our civil infrastructure, so I'm a geotechnical engineer, more adaptable. So can we make rather making a very rigid structure, can we make it more adaptable? And I think in building sector, that started to happen. Are we over-designing it? That means that we're doing 120 years to make it really, really strong. But actually, in order to do that, we need to understand the actual performance to improve our design. So at that London Bridge Station, we've been trying different things. Of course, 70s and now different is that we have an Internet of Things, a lot of things, technology that evolved in the past 40 years. So I'll talk about fiber optics monitoring, but you can do computer vision technology or count the people very quickly and then do some real-time monitoring movements. Wireless noise monitoring because they have hospitals around and make sure that the construction don't produce much noise. Social media tracking. And then, as a civil engineer, you want to use some movement and make sure that we do engineering analysis. So, for example, this one is really predicting during the construction how people are using the station and also doing an agent-based model to predict how people are using and trying to do that in more of a real time. So when the train comes later, how do people use the station, and then can we divert the people in a better way? And that started to happen using these sort of simulation techniques coupled with monitoring of people. This is a Twitter usage of that station, and you can see this is one day, sort of frequency, and then it shows a peak in the morning, and then in the afternoon when you go back home, it peaks another one. Which one is a Twitter and which one is actual counting? And the red one is the Twitter, because Twitter people come late to work. They may go later and have fun. But then you can get the data quite without using much sort of manpower. Looking at the Twitter data, perhaps you can see how stations are used. So you can start using all these sort of techniques, like this is a sort of a web geo-base that we're looking at London as a city, as a sort of a transportation network, as well as the railway network, how people are using. And nowadays you can use Transport for London data or sort of a Google data. We accumulate all these together. And then behind that, we start to look at the scenarios. For example, what if we close Westminster Bridge? There's a new agent, so if you have new railway lines, if you have autonomous vehicles, smart data travels, how do people do? And then you can start looking at how in terms of policy-wise. But it's really trying to figure out value of sensing, because you want to put sensors, like me, I want to put sensor because that's my research. But then people say it's too expensive, but then you have to start showing the value. And I'll come back to this value more. But you can see that how interesting the computer science is coming into, of looking at lots of data of different things. And some data comes every second, some data come every year. So for example, we're looking at road maintenance. This is agent-based model. Basically, you have agents within the city and then see how macro behavior addresses the macro behavior. And these are very computer intensive. By using high-performance computing, it starts to become realistic using crowdsourced data. So these are interests to our civil engineers. So for example, if you have these data, can we do sort of road degradation better? Because at the moment in London, we only have data every year, one particular point every year. And it would be great to see how people are really using the road and then how they're reporting, but also see the real degradation of the road or railway using those data. And that leads to another technique called cellular automata. It's really a sort of a land-based, sort of a agent-based model trying to see how the roads are degrading and that sort of thing using a sort of crowdsourced data. So that's something we want to go further in civil engineering. But what I want to go back is that I'm trying to introduce today is really about sensors. So this is a center that my colleagues and myself developed 5 years ago at Cambridge University, Cambridge Center for Smart Infrastructure and Construction. Mission is about transform the future of infrastructure through smarter information. Really to enable step changes in construction practice, making a world-leading sensing and monitoring industry, in this particular case in the UK. And then our real goal is about asset life extension and reduce management costs. In a sense that you put some money in, but then you have to have a big benefit. And how do you count that benefit? It's quite challenging. The phase 1 is just finished, and then I still work together with them on phase 2, which will go for another 5 years. It's really working together with industry, looking at infrastructure owners. So you can see London Underground and other infrastructure owners. So in this California, it will be like Caltrans and PG&E. And then you have companies on the construction sector. But important thing is that we work together with the sort of IET areas in terms of sort of Toshiba, Topcon, or Thales, these information or technology providers. And working together with, of course, with the policymaker, which is Infrastructure UK in the UK, which is the government body. And it really about the strategy is having a sensor data, helping us to understand the asset like bridges, roads, or tunnels in terms of data analysis and interpretation. That will lead to how do you manage your asset. And once you know how your asset manages, that the city will have different assets. So how do you combine these together to look at whole city? And there are a variety of questions that you can think about at different scale, but it's really our interest is really how these data come across throughout the scale. And that's the challenge, but that will be our interest as a civil engineer. When I was at Cambridge, and I continue to do so, we've been working on low power, ultra lower power wireless sensor network. I'll talk about distributed fiber optic sensing because this is quite interesting technology from my point of view, computer vision and robotics. So for example, in computer vision and robotics, computer vision is quite interesting for civil engineers because if you go to a tunnel, each concrete panel looks very similar to you, but from the computer vision point of view, it has a fingerprint. So what you can do is that if you have two images looking from different angles, actually you can match the fingerprint from different angles, and by having picture taken from different angles, actually for a given point, you have 3 images or 2 images, you can triangulate to create a 3D model. But also you can see where your camera were taken, where your cameras were at that time. So that allows you to start creating a model just from images. So really taking images, this is a work closely with Toshiba, and then reconstruct 3D points, which just from the images you can create a 3D model. And then you can start to see how the model looks like. So you can see some of the cables which you don't know, so you don't need, so you remove it. But you can see a very detailed sort of a structure component just from the images. And then you create a 3D model for you to do engineering analysis. Important thing is that after that, actual 3 images will have 3D points. That means that you can attach the images on top, mosaic it in terms of images, and put it onto your sort of a cylinder in this particular case. And that gives you a map of your tunnel with images which is very, very highly precisely calibrated in terms of the coordinate system. Once you do that, actually you can have like that, and then like a globe, you can make it flat, and you can make it flat like this. But then each point has 3D points. So let's say if later on, if you take another image, sort of about 1 year later, you may have a new splash over here. What you want to do is to compare with the images before, 1 year before, but then it may be taken at different angles. But because each have a coordinate point, what you can do is that these old images can be warped to same position that the new images are taken. So actually, where you're looking at, this one is rotated in a certain way that you're looking at this image from the image that from the direction you're looking from the new image, which allows you to do a change detection. And so in tunnel engineering, what we're interested in is cracks. What kind of cracks we're interested in? Actually, we're looking at 0.3 millimeter cracks. And are they growing or not? So these are the sort of like scale that we're interested in. We're not interested in 1 centimeters or 1 inch. We're interested in really small movements. And what you can do now is that by doing that, you can start to do sort of take an image and then see how things are changing. And you can use certain computer vision techniques and machine learning techniques, perhaps, to trying to find out the change detection. And for example, these are the sort of splash marker, and then these are different algorithms to try to find out what is the change detection, which is ground truth versus some sort of analysis. This one is another ground truth. If you don't see very carefully, but there's a small fish that our student wrote on tunnel lining, but then it does detect. But for example, this one, we didn't do anything, but it did detect something. So still, there are a lot of ways to do, and my point is that nothing is perfect. And I think we have to do more research in this area, and I'm really interested in working with some of you who may be interested in this particular area. These are sort of sensors that we're very interested in, and of course at Berkeley they're famous in terms of some sensors and microelectromechanical system sensor MEMS. We're interested in measuring strain, which I'll talk about later on. But low power is quite interesting because by low power, you can start to use energy harvesting to power our sensor system and continuously measure our system. I don't want to have data every day. Some people like bridge bearings actually want to know how many times you had a small movements per day, how many you have mid one, and how many you had big ones. By number, how many numbers you had may be very interesting to us because that gives us how it degrades with time. But the point is that if you have one data, you miss that particular event, and then you're gone. So I think by having some information about the sort of history is very, very interesting for us. So that requires low power, but then energy harvesting can do. So for example, in our civil engineering, we use a device called vibrating wire strain gauge. This is a strain gauge, which is very, very robust. And what it does is within this system, it has a string inside. And if you strain it, pull it, or compress it, actually, when you play a guitar, if you tune it, you change the resonant frequency and gives you the different sound. So that's the same thing. If you stretch it more, the resonant frequency changes. And that's how it works in this particular system. And that's the same thing that we made a MEMS version of that. So this is a MEMS version of that, which actually, because it's small, but also it's sort of made in a certain precise way. This one may give you 1 to 10 microstrain. This may give you 1 to 10 nanostrain. Whether we need it, I don't know, but it'll be fun to see if you get the data. So this is, again, you have this sort of a structure made using MEMS device as technology. You have a suspended beam. And then these are the 2 points that will strain. And for those who are in structure mechanics, this is the one that could give you the vibration to see the vibration of that particular structure at different strain level. So my structure engineering colleagues will say this is easy to do the analysis. So this is really a small device. This gap is less than 1 micron. But you actually do a resonant frequency analysis of these devices at different strain level. So once you do that, actually, you have this amplitude versus frequency, and if you apply different strain, the peak frequency moves, and that gives you how much strain you applied. And you can do that, and by putting these devices at different directions, you can get strain at different directions, because, as you may know, strain is not only one direction. Actually, in reality, we have 6 strains in structural mechanics. But the point is that these are small devices. It can be just fun, but if you have a very good eye, it's moving. Can you see? It's an eye test, sorry. But the point is actually it has a very low power, which is quite interesting for us. So in this particular case, we made this device and put in a tunnel in Prague, in Czech Republic, because this particular tunnel was flooded in 2000-something. And then the issue is that after the flooding, how is the degradations happening? So we wanted to monitor. So there's a crack over here, which above here we had this crack gauge, which is a simple crack gauge. But it did have this MEM strain sensor, which is aligned this way to understand the crack is really opening or is it sliding relative to each other. And then you can make it as a sort of a chip, which we're trying to do at the moment. So if you have a sort of a strain or accelerometer, you see accelerometer and kilometer. Some of your iPhones do have these accelerometer with cheap ones already, and they're very cheap. So you can make the strain. I haven't seen much in the market, but we hope it will come in. But if you have these small, sort of a low power sensor, energy harvesting like vibration, temperature, pressure fluctuation, airflow can power it up to get the data. And once you need the data, you may send it wirelessly. So in terms of power, there are a lot of ways to get power. If you walk, you can get power. Water mains, actually, if you look at water mains, water pressure fluctuates in a very low frequency, but you can sort of ramp it up to get this pressure energy, like winding your clock, for example. You can have a solar power, but in tunnels, which I work on, it doesn't work. And then airflow is good for tunnels because I'll show you later on when train passes you have flow. And then vibration is another one, but temperature is also an interesting one as well. So this is data we measure in terms of airflow in the tunnel. Actually, it flows. This is at different times, and every time train passes, you have a flow. So you can have a miniature turbine, which you can power it up. And it gives you about 0.3 milliwatt of a cross-section of 1 centimeter turbine, for example. That may be good enough for getting data. Tunnel do vibrate, so you can have a vibration and then trying to get energy through that and then keep on monitoring your infrastructure through that. Vibration is very interesting. So I'm not sure you've been to London. If you go to Tate Modern, which is a very nice museum, which is over here, they made a new Millennium Bridge in 2000. The bridge was interesting because when they start opening, people start walking, and it wobbled a lot. So people are walking, and then bridge is moving a lot. But if you look very carefully, people are rather synchronized. Initially, they walk in a different way, but then eventually they synchronize. See? Can you see it? That's really interesting. And probably you may have seen this because some say they've seen it. Now, if you do, this is Professor Ikeguchi from Saitama University. He had a bridge with the metronome, lots of them. So you keep it going. You keep it going. And you keep it going. For about 2 minutes or so, it becomes like this. There are some odd ones. But if you see it, it will come together. So it's so fun, actually, in terms of vibration. That vibration is one of the systems that you can absorb energy, for example. Typically, when you learn about your dynamics in your first year mechanics, you look at what you call vibration, which is direct resonance. If you have a mass, if you have a spring and dashpot, which are your energy absorbed, if you move vertically, your mass will move vertically in parallel to your spring. And then that will give you some sort of a, depending on the stiffness and your mass, it gives you the resonant frequency, and it matches. That's what you absorb your energy through. The other one is called parametric resonance. It's actually you vibrate in a horizontal direction. And that is shown over here.
When a pendulum is allowed to freely swing, it oscillates at the natural frequency, as you can see in the horizontal direction here. As I apply a horizontal driving force at this frequency, resonance is achieved as amplitude builds up. However, if I apply a vertical driving force at 2 times of this frequency, amplitude can grow even larger as parametric resonance is activated.
So it's a sort of a nonlinear vibration system.
Scale piezoelectric vibration energy harvester prototype mounted on a mechanical shaker. It is currently driven into direct resonance. Take a note at its displacement amplitude.
So this is direct resonance. Now this is the parametric resonance.
The prototype is now driven into parametric resonance at the same acceleration level. With time, the oscillatory amplitude grows to a much larger level as an internal energy buildup is achieved. This demonstrates the superior efficiency of parametric resonance over its direct counterpart.
So that sort of interesting nonlinear vibration can be used to absorb energy, for example. If you don't believe me, I brought a yo-yo, so you can have fun later on. That particular device is shown as a yo-yo, and then, of course, there's a threshold that you'd have to kick in, and then that's where you have your engineering. How do you make that threshold smaller, and then you make a macro device. So this is one of our macro device that has that yo-yo inside, but it's not yo-yo. So these are things that you can make it at different shapes or sizes depending on your need, but of course, bigger the mass, you can absorb more energy, as you know. But you can make a MEMS version of that, making a smaller version of MEMS and trying to make it as that, and you can have lots of these to generate enough energy to power, for example, this MEMS strain device. And actually, we spin out this particular devices, so we have a company called 8Power working on that. So what I wanted to really try to say in this particular talk is really value is not a product for our point of view. It's about confidence in delivery in civil engineering. So I can't sell you the product by doing TV commercials. I just have to do a lot of things to demonstrate it works in the real field and that sort of thing. So my colleagues from London Underground, Keith Bauer, says that innovations have more chance of adoption if their benefits are mapped. We have to show where the benefits are coming. And rather than just saying, please buy me my product, it's really trying to, you're going to get this data, and this data will give you this. And of course, best practice, guys, is very important. So me and my colleagues wrote 2 books recently on distributed fiber optic sensing and wireless sensor network, which is published through Institution of Civil Engineering publication. What I want to focus today in the next 10 minutes or 15 minutes or so is one of the technique called continuous strain profile using fiber optics technology. So this is a typical optical fiber, which I have it over here. So I have different types of cables because some are cheap and some are expensive, but I can pass it to you around. Yeah. So this, the white one, you can do anything because it's the cheapest one. But then the expensive one, actually, you can't do anything because it's so robust. So the point is that you have an optical fiber, which is a standard optical fiber. It can go to 10 to 30 kilometers. You shoot a light. And then what happened is that we have a technique to measure strain or temperature or other things, or strain and temperature in our cases, measure every 5 centimeters, which is every 2 inch, gives a data of strain and temperature at that particular point throughout 10 or 30 kilometers. So it gives you a distributed strain or distributed temperature. that means that 1 kilometer, if you have, say, 20 points per meter, you can have 20,000 points per kilometer. Lots of data of strain and temperature. How does it work? Oops. This is an optical fiber that you're seeing around. It's a core which shoots a light and the light goes through. And then you have a cladding that protects to make sure that light doesn't go away. And then the light goes through mostly through here. And then you have this buffer or coating material that protects from this particular important fiber optical cable. Within that, as the light goes through, you have a density fluctuation of impurities, and therefore you have what is called backscatter light. And with the combination of acoustic wave and the light scattering, there's a scattering technique which I can't go in detail. But the basic thing is that you shoot a light, every point you get what backscatter light. So for example, it's not quite true, but if you look through the window, most of the thing you can through the window, but sometimes you can see your face because your window is dirty, for example. But that's the impurity gives you that particular thing. So if you shoot a light, you have every point coming back. I know where that light came back from because speed of light is constant. So speed of light times delta t divided by 2 is where that light came back from. So if you shoot a light, the one comes earlier is that coming back from near your place. And then you can get the backscatter, and then backscatter light, I can look at the frequency content. And there's a variety of nonlinear and linear scattering process, and one is called Rayleigh, which allows us to hear the noise, which is acoustic. There's a one called Brilliant, which allows us to look at change in strain and temperature as the frequency, peak frequency changes, like your resonant device. And then Raman, which is very popular nowadays, is to look at how the temperature changes by looking at the amplitude change. And that allows to measure temperature variation or strain variation throughout the cable for 10 kilometers or so. Very nice. So you shoot a light, and then let's say if I have a strain over here, the frequency shifts, and that's what I want to measure. So if I can measure that, that gives me a sort of a strain is being strained over here. But I can do that for all the places. So that is what the analyzer does. So the analyzer can be expensive. But before I say that, there are cables like this. The white cable that you've been seeing, which only has 1 millimeter or 0.9 millimeter diameter, it's probably about 10 cents per meter. The very robust one, which went to use in our civil engineering, is about $15 US per meter. Why? Because probably we're the only one that use it. So if all of you start using it, maybe it's okay. But this one is good because you have the optical fiber coated around the sort of a strong nylon with a steel wire to protect things. And you can get lots of different low robustness versus high price, but it's about how you embed these in the structure. So for example, when we make tunnels, we excavate the tunnel and we do what is called spray concreting. So that is spray concreting to a concrete structure, and we embed the optical fiber, which is a robust one, and then if we spray concrete, we make a concrete block, which is fiber is embedded, and they happily survive. Analyzer is expensive at the moment. It probably costs about 100K, 200K each. So within my research team, about 5 years ago, I said, I can't pay 100K every time I buy these. So I said, let's make our own. So now we make our own analyzer as a research tool. And now we're going to more dynamic sensing. So previously, people were measuring static strain because it takes about a few minutes or so to take the strain profile for 10 kilometers or 30 kilometers. Now we're trying to go dynamic strain and measuring strain profile dynamically up to 100 hertz, which we're interested in civil engineering. So that gives us a little bit more, can we look at more vibration characteristics as a distributed strain, not like a point strain. Just to give you some nice example, this is London again, sorry. This is a masonry tunnel, which is 100 years old masonry tunnel. This is called King's Cross Station. This is St. Pancras Station. If you want to go to Paris, you take St. Paris from St. Pancras Station. You take a Eurostar to go Paris. If you want to go to Harry Potter World, you take 9 3/4 from King's Cross Station. But that's where it is. But the point is that this particular station was part of this Eurotunnel construction, 100 years masonry tunnel, where there are new tunnel going underneath diagonally. And then this clearance about 3.6 meters. And you can see there's a water canal around over here. And we don't know why, but the engineer thought it would be good to put the foundation of that water canal on top of that 100 years masonry tunnel some time ago. So you can see how you dig it. This will distort this tunnel. It may get flooded. You may get disturbance to your existing tunnel and all these things. So what you can do is that you can attach the optical fiber like this in cross sections. In this case, 5 different cross sections and 3 longitudinal directions. You attach the optical fiber. This was our early days, like early days of our research, about 10 years ago. So you can see a white cable. Can you see a white cable? Maybe you can see that's our cheapest white cable. And then we went to DIY shop, bought this hook. You drill the hook, and then you pre-tension it so that we can measure tension and compression. And measure it throughout. So everything is one line. It sort of combines to one line, and it goes to the analyzer. So what I'm going to show you next is an animation where when you have a new tunnel, old tunnel over here, and when the new tunnel is made, the new tunnel drags the old tunnel downwards. And what you do is that this tunnel will get vertically elongated. And what happens is if you put that cable around the tunnel, you see a tension over here at the 2 sides and compression at the top. So the distributed strain profile will look like this with distance from the west wall to the east wall to the top of the crown. Tension, going down to compression, and coming back to tension like a butterfly shape. And then because the tunnel is not excavated underneath, sometimes it goes to the side because it's going diagonally different. So sometimes this position will move to the left and right depending on the position of your tunnel. So this is the animation I'm going to show you. This is the old tunnel where we had this 5 cross section. And the new tunnel will be excavated underneath. And these are the graphs of 5 graphs of 522, 520, 518, and all these things. And this is this initial strain profile, which is 0. We baseline it. And when the tunnel is made, these will start to respond. And 518 is the one that goes underneath, so you'll see that butterfly shape, hopefully. Now, the strain level is 0.1, 0.2%. We get worried about 0.1%. But the plot I'm giving you 0.2%, that shows you something that it did go more than 0.5%. So tunnel is moving, excavating underneath, and it just passed 522. So it just passed 522. Can you see a little bit of tension, compression, and small tension? And more tension over here because it's on this side. And you can start to see 520 showing a similar thing. Just past 520, it goes like that. 516. And 514. So it allows you, if you only have few points, it's very difficult to understand the mechanism of how tunnels are moving as the new tunnel is going underneath. And that's the sort of a beauty of this technique, is that you can get a distributed nature of the movements. And then it also looks at how much strain is developing. So this side is about less than 0.1%. Here you start to get a little bit larger. Here, look at this one, it goes 0.2%, but then it goes down, implying that when tunnel, the critical moment is that when tunnel face is right under where you're interested in. And as it passes, you have less strain. So distortion is when your tunnel goes underneath, which is obvious. But then you start to get the mechanism. So you can put this in piles. For example, this is, sorry, I'm a geotechnical engineer, so I'm interested in underground. So you put fiber optics in the piles. And then you put everything together, and then you put your monitoring somewhere else. Oh yes, and I have to protect my analyzer because it's very expensive at the moment. So this is a project in Canary Wharf, which is one of the big financial sector of London, where they're making big buildings, and then you can see a foundation where you have piles going through 50, 60, 70 meters. And these piles are about 2.4 meter diameter, so very big. And these are the normal things that we do in civil engineering now. And you go down, but you can see there's existing London Underground tunnels. So the point is that you don't want to bring the stresses to these old tunnels. So we tend to sleeve around and then make the building low go into the chalk in this case. But we want to know how much friction can you have and what end bearing you can have in these piles. So what you can do is that you can do loading of the system and then measure how things are going. This is one of the techniques called O-cells, where actually you load the pile. These are sacrificial piles. So you load the pile to see how pile responds to loading. So I'm putting a load over here that will push the pile upwards, but push also pile downwards. And that by pushing upwards, I can see how much friction I can develop between pile and the soil. And that allows us to make a design of these piles. This one pushes down, which will give you an end bearing of the pile. So how much we can resist at the bottom. Now, this is done quite cleverly because the load is self-reacting each other. Think about if you want to do load testing from the top. You have a large load of a 50 or 60 meters diameter long pile with 2.4. You're going to have a very big loading system. It's going to be too expensive. But this allows us to measure the sort of friction and that sort of thing through that system. But the point is that you have to install your fiber optic cables. So you put your cable over here. These are cages. So you drill the hole, and then inside the hole, it's filled with what is called bentonite slurry, which is a very heavy liquid, to make sure that the hole doesn't collapse. And after that, you put this steel cage in, and after you finish this steel cage in, you pour the concrete from the bottom and then create a pile. And that's how we create a pile. So probably for those who are not civil engineering, you might now find out how you make piles. Interesting, isn't it? But the point is that when you make this optical sensing instrumentation, these guys who are making the piles are not interested in fiber optics. They're interested in making a pile and go home. So important thing is to make sure that you don't disturb these guys. So one approach is that, okay, we have a cable like this, put in a drum, and as the cage goes down, you roll in. And as the cage or splice, you clip and goes in. You clip and goes in. All these guys can do it, and then they go home. Cambridge University academics at that time don't have to do anything. And that allows us to get less disturbance. And actually, they start to like this technique, which I'll show you why it is. But the point is that's how you do it. And you put this sensor in the concrete, and then you do the loading. If you conventionally want to measure strain, you have each strain sensors coming out with each cable. So if you have a pile like this, we tend to have 6 levels, 4 each level, so you have 24 cables coming out. It may look like this. But if you use fiber optics, it looks like that. So it's clean and nice. Of course, you have to make sure that it doesn't break during the construction. So the point is that you have this sort of a pile. This is what we call tremie pile, where you inject your concrete, and then as you lift this pipe, the concrete fills in this particular place and then create a pile. And this is the cage that looks like at the bottom, and the optical fibers are attached at 4 different locations. And what you can do is that you can have a cable that goes in and out. So into the ground, bottom of the pile, goes up. Oops. And then you do the same at different locations. You go down and up at different locations. And you go down and up. And then you can change it to strain cable that goes down and up and that sort of thing. So you can measure temperature and strain. The reason why I need temperature is I have to do temperature compensation, as we do with any instrumentation. But the point is I can get a temperature profile and strain profile at different loading stage. So this one shows how temperature is changing as the concrete is curing. And you can see, I'm not sure you can see, there's a blue and green line, and there's a red and yellow line, which on one side, on the other. Which means that the inside of the pile, concrete is not curing homogeneously. And that is different from the top and the bottom. So it starts to show that there's something interesting happening in your pile without you knowing it. This is when you do the loading stage. Loading stage, as you increase the load, you have larger strain around the loading stage, and then it decreases because friction is developing and strain decreases as you go up. So this is normal to our pile design. But again, you can see something like that. But when you see it, when my colleagues saw this, I said, oh, Kenichi, I don't like this data because it goes up and down and up and down. And typically, if you're paying somebody, say, I don't like the data, I'm not going to pay you. But the point is that this one is interesting because if you see the temperature at the beginning, it also shows similar sort of frequency, which is about 3 meter frequency, which is different from actual frequency you can get from the random noise of the analyzer because you're getting every 5 centimeters. So these are much larger frequency than the others. But by having a temperature, the worry is that, is my pile like that in the ground? So that's where you start to be interested in when you look at the construction, can we get these data and trying to understand the quality of the pile? And with the temperature data, actually I can start to guesstimate what the shape of the pile is as it propagates throughout. And that allows us to look at fiber optics shape versus we had another system called sonic caliper logging, another way of measuring it to get that. Now this is interesting because now you can start to look at the quality of your infrastructure. Now in the construction process, we have what is called sonic logging, where we have a pipe, another pipe inside, and we do ultrasonic logging to look at the quality of the pipe. The problem is that this pipe goes installed inside a cage. So when the construction workers try to splice the pipes, when the other cage are spliced together, you have to put your fingers inside. And then sometimes they cut their fingers and lose fingers. With this one, you don't have to do that. So the construction workers at site said, oh, I love this device because I don't have to cut my fingers anymore. So again, my initial interest was oh, I like this data. But actually, the driver was people like this one more because the demand was different. And that's where the value comes from, is that I thought value was this. Of course, it is important, but more interesting value was this. So what I wanted to say was that is it potential for whole life management, construction quality control. You have a cable inside. You can see actual load coming into your pile. And then if earthquake happens, is my pile broken? You can check again. Or nearby construction, you can do future proofing. So we've been doing this for many, many sites. And this is one of the examples of fiber optics, but you can do for deep circular shaft. You can do for slope movements. And maybe you can do for pipelines or these things. These are for tunnels, for cross-passage openings. So these are things that you can do once you start thinking about putting optical fiber at different locations because you can measure lots of things in one single optical fiber that you see in front of you. So fiber optics coming. So think about your nerve system, a bit like your fiber optics. Putting these in your infrastructure and that sort of thing will be an interesting thing. This is what we call Future Tech Hype Cycle, as many of you may know. This is the publication from New Civil Engineer, which is a civil engineering journal in the UK. And of course, when you start your project, you're somewhere over here, which is an innovative trigger. And you have lots of expectation, and then people will give you funding to go over here. But suddenly it drops because it doesn't look real. And then if you work very hard, you start to go over here and comes back again. And fiber optic sensing within our field, we think it's around here already. It took me 15 years, but that's life. Right. So what I wanted to finish off by saying is that smart infrastructure is not an isolated subject. It's about, I told you a little bit more about civil engineering today, but we're interested in Internet of Things, pervasive embedded sensing, high-value manufacturing, data, smart cities, and then BIM is called Building Information Modeling, which really brings everything data together, and that is smart infrastructure. So hopefully that makes sense from your point of view. I know you come from different backgrounds, but this is what we're interested in, and if there are any opportunities to work together, please let us know, and then I'm more than welcome to talk to you. Thank you very much.